radiation intensity of an antenna is denoted by, say, U is equal to uh, cos to the power 4 theta sine square phi, right, with 0 less than or equal to theta less than or equal to pi by 2 and 0 less than or equal to phi less than or equal to 2 pi. Find the directivity, right? On very standard question. Just remember, uh, first I am supposed to find out the what is called as the power radiated should be calculated first. Okay, so this is what you calculate. Always some U is given, you are supposed to find out the directivity, right, by using the following this thing, right? So this is, first you calculate power radiated by this antenna, so you denote this as PRAD. This is the equation. So double integral, one integral for theta, just write whatever theta it is. It's 0 to pi by 2 in this case. If it is a different one, you will put that. Okay. And the second one will be for phi. Phi is equal to 0. In this case, 2 pi, correct? 0 to 2 pi, right? Write the function. The function will be whatever is given, right? So okay, I'll first write a general equation, that is U into d omega. Okay, this is the general equation where the U is what we already know, right? U is given, so that is equal to, so I'll slightly make a difference change here. So it's you don't have to write a limits for the, if you are writing U format. So double integral U d omega is the equation. Now we'll do the mathematics. So P radiated is equal to, do the calculation. This is for theta. Theta is equal to 0 to pi by 2 and pi varying from 0 to 2 pi. So what is U? It is cos to the power 4 theta sine square phi. Then d omega is nothing but sine theta d phi. Okay, sine theta d phi. Okay, now since it's in the format of a product, right, you can directly split it and write. So that this is equal to, so integral, so let me try to write this. So let's split. So this is theta is equal to 0 to pi by 2. That's the first part. Bring the all the terms that containing theta to ones under this. Okay, so that is cos to the power 4 theta into sine theta d theta. And second integral for phi is equal to 0 to 2 pi, it is sine square phi d phi. Okay, now this becomes a simple double integration problem. That's all. Okay, so what we do, uh, if you remember, the sine square phi is an even function, right? So even function means I just have to substitute. I have a direct answer for this. So let me show you that here on this side. So that means integration 0 to 2 pi sine square phi d phi, right? This is equal to 2 times integral 0 to pi sine square phi d phi. So sine square theta can be substituted as 1 minus cos 2 theta by 2, correct? So that is 2 times integral 0 to pi sine square theta is 1 minus cos 2 theta whole divided by 2, right? uh, d sorry, it's a 5, my mistake, just write a d5. All right, so 2 cancels. Okay, so that means it's I substitute 1 becomes integration becomes 5 minus cos 2 theta is sine of 2 theta by 2, and you substitute 0 to pi. When it means it is pi minus 0 for the first term, minus for the second term, sine of 2 pi is 0, sine of 2 0 is also 0, it's simply pi. Okay, so that's the calculation. We can do it separately and we can bring it back into the equation. So I know that this whole term is pi. Okay, so I'll write a pi there, so that's a pi. So that is equal to pi into, right, the remaining term. Okay, so that is theta is equal to 0 to pi by 2 cos to the power 4 theta into sine theta d theta. So what we do now, we have to go for a substitution method because there is no standard standard answer for this. So put let's say x equal to cos theta, right? So you differentiate to get on the side it is dx equal to differentiation of cos theta is minus sine theta d theta. So wherever I see a d theta, I'm going to replace it in this way. Okay, sine theta d theta is minus dx. Okay, that's what is my first thing. And we need to calculate when theta is equal to 0, what happens to x? It's cos 0, so it is equal to 1. Okay, and theta also goes till pi by 2. This means x is equal to cos pi by 2, which is 0. So 1 to 0. So this implies I'll write the integral now. So on the left hand side, I'm still calculating the p radiated power. So that is p radiated is equal to, so make a substitution. So pi is there as it is. It is integral from x equal to, starting from 1 till x equal to 0, right? Cos power 4, that is x to the power 4 into sine theta d theta is minus dx, because dx is equal to minus sine theta d theta, but I don't have a minus over there. I have sine theta d theta, which I can write it as minus dx. Okay, so that's my term. So that I can try to write it in this way. So I can rewrite this as pi. I can cancel the negative. Minus dx can be cancelled directly by making this change. X is equal to 0 to 4, 0 to 1, x to the power 4 dx. So what is that? That is pi into x to the power 5 divided by 5. Substitute 0 to 1. Correct? So pi by 5 into, when you put 1 to the power 5, it is 1 minus 0 to the power 0. So this is simply pi by 5. Okay, right. So we calculated the radiated power. Okay, then directly we can use the radiated power to calculate the what you call directivity. Therefore, the directivity capital D is equal to 4 pi times the maximum intensity, that is um, divided by P radiated. Now you see, in a question, if the is mentioned, you use that. Otherwise, use to be equal to 1. This is the standard value for isotropic antennas. Okay, so isotropic radiators will be having an we assume that they have a value equal to 1. That's a normalized value. Okay, so always, if it is not given in this problem, not given, directly use it. Okay, fine. So this is equal to 4 pi into 1 divided by pi by 5. All right, so this cancels. So you have an answer that is equal to 20 is the required answer. Okay, very standard procedure to calculate this. Okay, do you have any doubt in this? The procedure remains same. Since time is less, I will not solve more problems on this. Is it okay? All right, let's move further. So almost all the fundamental questions will be based on this itself. Okay. No, UM is given means you have to use that. If the UM is not given, you can take it as one. Okay. Right. So that's the standard procedure. Another version of the question is there where you see they give an equation like this, right? This itself, sorry, whatever u equation given there, right? There you may have, right? Here itself you may have a present. Cos to the power 4 theta sine square theta, right? It's possible. If that is there, you will see that gets cancelled. You don't have to substitute a here, because my answer will be something like pi by 5 in that case. Okay, that will come to the denominator and cancels. Right, right. So either it's this way, or if it is not given, assume equal to 1. All right. So that's the standard procedure we have. Is it fine? That's fine, right? Okay, let's move further. The next possible question here is about the efficiency as well. So we need to calculate the directivity and the efficiency of an antenna. Okay, next question. Antenna has radiation efficiency. Not efficiency, by mistake. The efficiency is a question. Radiation resistance. Radiation resistance of 73 ohms, and it has a loss resistance of 7 ohms. All right. If the power gain is 20, calculate the efficiency and the directivity in decibels. Okay, so let's quickly write what is given. One is called as RAD, radiation, that is 73 ohms. Another value R loss equal to 7 ohms. And another one is GP, is a standard notation. If you read the theory, you will come across this. It's a power gain. It's 20. Okay, so first directly we can go for efficiency. Efficiency eta is equal to, this is P radiated divided by this is the actual equation, P radiated divided by the P radiated plus P loss. That's the equation. But you see, when the power is not available, maybe you have done a derivation in the theory that you can even use R radiated divided by, this is R radiated plus the R loss. So simply substitute, this is 73 divided by 73 plus 7. So 73 by 80 comes to be 0.9125. In percentage, this is 91.25%. That's the efficiency, direct equation. Okay. All right. That's one equation. Then, okay, we can try to represent. Okay, there is another equation to relate the power gain and the directivity. Okay, so just recall the GP is the power gain. Okay, GP is a power gain. You can see that it is given as well here, right? So you can see that power gain is 20. Okay, right now, so we use the power gain. So GP is equal to the efficiency times GD, right? GP is the, anyway, we know that it is the power gain. So GD is the directivity, is a directivity. Or you can simply write D. That's also fine, because some of the books follow GD notation. Okay, I'll use the D itself so that it becomes easy for you to forget. I don't have to write what is GD. Just remove this, no problem. Okay, so this is what is given. Now the question is to find D, correct directivity. This implies calculate directivity. D is equal to the GP divided by its efficiency. So that is 20 divided by 0.9125. I think this is approximately 21.92. Again, they are asking in dB. So D in decibels is equal to, it's a power, so 10 log. Remember, not 20 log. Okay, 10 log to the base 10 of D. So that is 10 log to the base 10 of 21.92, approximately 13.4 decibels. Okay, now okay, the next question is based on finding out the effective aperture. That's also important. Okay, the next question is based on that. Okay, find the maximum power gain. Yeah, find the maximum power gain antenna and effective aperture. Effective aperture if the diameter of antenna is 3 meter, operating at 5 gigahertz. Right, so you see, this is the given data. Frequency is given 5 giga, means it is 10 to the power 9 hertz. That's the one thing given, and the diameter is given. This is 3 meters. Okay, and okay, fine. So what we can do here is there is another equation for directivity. If you remember, that is 4 pi times aperture effective. Okay, effective aperture divided by the lambda square. Okay, so there is an equation like this, but I need to first find out the AE first. So uh, this is what, this is D. Uh, the D itself. Now actually, you see, this is actually a twisted question. Here they are not mentioning about a loss, right? Because actually, we need to find out what is the there is one equation. So actually, I'm not able to cover the theory right now. So you see here, there is an equation. The efficiency is equal to, we know that this is GP divided by D, correct? Just now we understood that. But I actually I need to understand how much is the efficiency of this antenna, then only I'm able to relate something. But it's, as I told, it is a twisted question, right? So whenever questions like this come, we need to assume that maybe I think nothing is mentioned about the losses, right? So I assume, right, loss is zero, so P loss equal to zero. That's why I'm writing efficiency equal to 1. Okay, it's a efficient one. So now you see, when this is zero, this implies, so the, you see, the question is maximum power gain, that itself is the directivity, correct? Because D goes to the other side. Right, so that's why I'm able to even calculate D here to calculate the GP value. Okay, so the question is to find GP, but you see, I'm still using the D equation to calculate that in this particular problem. Okay, so GP equal to D. So this is what is a twisted part. All right. Okay, so that's why I'm calculating D. So this itself is the maximum GP. Okay, right. So that's why I'm using this equation. Fine. Let's go ahead. So that is equal to, I need to calculate AE, right? AE is nothing but your aperture, that is pi r square. Diameter is given. So let's calculate AE. AE is equal to pi r square. R is equal to D by 2. D is given. Okay, D by 2 whole square. So that is pi into, this is 3 by 2 whole square, 1.5 square. Yes, yes, yes. You can use either of them, right? Whatever you are comfortable, you can use. No problem. Right? You will get the same answer. This comes to be approximately 7.0685 aperture, so meter square. Okay. So I also need the lambda square. Frequency is given. Convert that into lambda. So lambda is equal to C by F, right? So 3 into 10 to the 8 divided by, what is the F given? 5 into 10 to the 9. Okay, so this is approximately 0.06 meters. Okay, substitute this. So GP is equal to 4 pi into the aperture, that is 7.0685 divided by lambda square, 0.06 the whole square. Okay, so the power gain of this particular antenna is something around 24,673.7. Okay, this may be even sometimes they ask even in the decibel scale. Anyway, we can convert that. Okay, all right. I'll move further. The next question. This could be a short question as well, right? Okay, this is calculate the directivity. Calculate the directivity if the half power beam width in perpendicular planes intersecting beam axis are 35 degrees and 40 degrees. Okay, so you see there is one equation. This should be there in your theory part. So directivity D can be calculated by using 41,257 divided by the theta E and theta H. Okay, one is the with respect to intersecting the beam axis, two angles are given 35 and 40 that are theta E and theta H. So if you remember, the theta E and theta H should be substituted in degrees only. Okay, not converting into any other format, not in radians. So directly substitute 41 257 divided by, one is 35, one is 40. Okay, so that comes to be approximately 29.47 is a directivity. So again, they can add up a question to this. They give a frequency and ask that find the aperture. Okay, absolutely fine. If the aperture is asked, you use the same equation. Effective aperture is right. Just now we use an equation wherein we had a lambda in the denominator. Lambda square d divided by 4 pi. So some frequency is given 5 gigahertz. Calculate a lambda from that and substitute here. D is known, lambda is known, 4 pi. Right? Simply calculate, you get a effective aperture of that particular this thing. Okay. So that could be the extension, the extended question which you might get over here. Okay. Next question. The antenna receives maximum power of 2 microwatts from a transmitter. Okay, I'll just write it EX, right? Okay, the question is to calculate the maximum effective area if the magnitude of E vector is 50 millivolts per meter. Okay, so you see that this is given, P received is given, it's a maximum value, so 2 microwatts. Okay, so I need to convert this into the what you call average power first. Okay, because there is a definition, the definition of maximum effective aperture area uses one of the definition uses received power by average power, right? So first let us calculate the average power. So what is P average? P average is equal to, this is the equation. Okay, just remember, magnitude of this E square divided by, this is eta naught. Eta naught is the standard resistance. Okay, 120 pi, if you remember, right? So that's the one. So this is half into, so 50 milli, 50 into 10 to the minus 3, the whole square divided by 120 pi. Okay, so that I don't have answer with me. Let's quickly calculate. Yeah, the eta naught is a standard value which is 125. That is called as a radiation resistance. Okay, standard value of the radiation resistance. So the notation is eta, but still it is not an efficiency. Okay, it's a radiation resistance. If you want, please note. Right. So I think this comes to be 3.315 microwatts. Right. Now we'll go for the effective AE. This is equal to the PR divided received power divided by the average power. So it's given as 2 into 10 to the minus 6. Now we get 3.315 into 10 to the minus 6. So anyway, this cancels 0.603 meters square. Okay. Okay. Next question. If noise figure of antenna at 290 Kelvin is 1.1 dB, find the effective noise temperature. So they have given the room temperature, that is 290 Kelvin. Okay, we want in Kelvin, even if it is given in the degree Celsius, remember to convert. Okay, that's the first part. Then they have given the noise figure. If you remember, the notation is F. Noise figure is 1.1 decibels. Okay, but in order to substitute in the effective noise temperature, this F should be uh, in the normal format, not in the decibels. Correct. So normally you see this is the equation. 1.1 is equal to 10 times log of F. Right. This is F in dB. This is the normal F. So I have to calculate what is called as an anti-log. That's all, right? So 10 to the power, you can do this. So that means F is equal to, so I have to take anti-log. I'll write anti-log, right? It's actually 10 to the power, right? Anti-log to the base 10. It is, you can do 1.1 divided by 10. So, right, 10 to the power this number. That's all. 1.1 divided by 10. That you raise 10 to the power. So that is 1.28 approximately. Right, anyway, so once you know this, you can calculate the effective noise temp. No, it is 10 to the power this number, 1.1 divided by 10. Okay. So that whole antilog to the base 10 is 10 to the power. Okay, in calculator you have to enter in that way. Okay. Okay, so that means we get 1.28 as the F in the on the normal scale. Now you use effective noise temperature equation, that is TE. Effective noise temperature is equal to whatever F you got minus 1 times the room temperature. Whatever temperature they mentioned, that temperature. That's I denote it as T naught. So it is 1.28 minus 1 into the 290 in Kelvin. So approximately that comes to be 83.5 Kelvin. That is the temperature. All right, let's move to the next question. Next question is this is about a power density. Okay, so find the power density at 3 kilometers from a source if the power density at 2 kilometers is 10 milliwatts per square, okay, meter square I can write. All right, SQM, that's fine. Okay, now we see we have an equation. The power density PD is equal to the radiated power P rad divided by 4 pi r square. Okay, so first I need to calculate the P rad now, because P D is given, radius is given, right? So at 2 kilometer, right, I know the power density. What is that power density? It is 10 milli. So 10 into 10 to the power minus 3 is equal to radiated power divided by 4 pi into, this is 2 kilometers. So 2 into 10 to the 3, 2 kilo square, right? You see, I have only one unknown here, that is radiated power. Okay, let's calculate this. That is 10 to the minus 3 into 4 pi into 4 into 10 to the power 6. That is approximately 0.5026 into, yeah, here it's something like, you see, you have a source here. Okay, this is the source, and you are measuring at a distance of 2 kilometers anywhere, right? So that makes a circle. So this distance, whatever you measure, itself is the radius. Okay, like that. So 0.5026 into 10 to the power 6. This is again power, right? So watts. Okay, radiated power is this much. Now at 3 kilometers, you calculate at 3 km, right? Calculate the PD itself. PD is equal to P rad. So that is 0.5026 into 10 to the power 6 divided by 4 pi into 3 kilometers. So 3 into 10 to the 3 square. That's all. Let's calculate this. This comes to be 4.44 milliwatts per meter square. Okay, you can see that this is much lesser than the 2 kilometer value. So at 2 kilometer, you were receiving 10 milli, okay, 10 milliwatts. But at a kilometer, at a distance of 3 kilometers, we are expecting a lesser value, and yes, it is correct. It's coming lesser value. So this is, you can say that this answer is right.